Hi, I just want to spend a couple of minutes today looking at something called standard form, which is a way in science and particularly in physics of representing very big and very small numbers. If we look at the number 10, no problem with that, it's quite easy to write, quite straightforward. But then bigger numbers become more awkward. There's more zeros here. It could become more time consuming to write them, so we actually get very lazy, and there is a shorthand way of describing very big numbers in writing and save some time. 10, 100, 1000 and 10,000. Let's look at another way of writing those. If we say 100 is 10 times 10, that's the same as writing 10 squared, and similarly 1000 is 10 times 10 times 10. So we could say that's the same as 10 cubed, and I could go on, etc. And I could write quite large numbers in this form, onwards and upwards, well, pretty much forever, all the way up to 1,000,000. I'm just looking at 10 to the 6. But we can go into billions and beyond here. It's really easy and straightforward to write these big numbers in terms of 10 to the power of 4, 5 and 6. It just tells us how many noughts are after the 1. So how might we do small numbers? If we look at the number 1 and divide it by 10, the answer to that would be 0.1. And there is a way of writing that. We could write 10 to the minus 1. It's been divided by 10, not multiplied by 10, divided by 10. I could go on. 0.01 equals 10 to the minus 2. 0.001 is 10 to the minus 3. 0.0001 is 10 to the minus 4, etc. So we have a way of representing very large and very small numbers relatively quickly in writing without taking up too much time, too much paper, etc. And there is another good reason. For instance, the speed of light, the fastest thing in the universe, has got a speed of 300 million meters per second. Or we could now write that as this is 3 multiplied by 10 to the power 8 meters per second. So if I look at an example, let's say gamma, there's the Greek letter for gamma waves. An example here, here's another Greek letter, lambda. We use that to represent wavelength measured in meters, and in meters the wavelength of gamma waves, well, they're approximately the same size as an atomic nucleus, 10 to the minus 12 meters. And if I say the frequency of a given gamma wave is 3 times by 10 to the power 20 hertz, that's a seriously big number. That's how many waves will pass through a point every second. Knowing these two things and combining with the wave equation, which tells us the velocity of a wave is the wavelength, lambda, multiplied by the frequency, I can use that to get the velocity. The velocity of a gamma wave is 10 to the minus 12 multiplied by 3 multiplied by 10 to the 20. That looks quite tricky, but I can actually do it in my head. Let's take this number out. 3 times by 10 to the 20 multiplied by 10 to the minus 12. These two numbers, all I need to do here with the powers of 10 is add these two numbers together. 20 take away 12. The velocity of light, velocity of gamma waves, is 3 times by 10 to the 8 meters per second. Okay, thank you.